In the previous chapter, we found confidence intervals for proportions, and in this chapter, we're going to find confidence intervals for means. So first thing you should remember is that the confidence level, say like 95%, this tells you the percentage of intervals computed using the same procedure that are actually going to contain the true population value. So the idea there is that if you find many intervals using these procedures, and of course new data, (95% of them will contain the true value. That could be the true proportion or the true mean, anyhow, it just contains the true value. And in the previous chapter, we found estimates of proportions, and in this chapter, we're going to find estimates of means. So before we get into the nuts and bolts of making confidence intervals, let's review some parameters and also discuss the kinds of things we're going to be finding confidence intervals for. So first, recall that a parameter is a fixed population characteristic, and you can't determine this because you can't measure all units in the population. Even things like a census don't usually actually get everybody. So to estimate this parameter, we use a statistic or an estimate from a sample. So that could be something like a mean, which is x bar, a sample proportion, which is p hat, or one of the other sort of 5 big things we've talked about this semester. Now the general format of a confidence interval is going to be the same as it was for a proportion. You have your sample statistic, which in the previous sections was p hat, or the difference of 2 p hats, plus or minus some multiplier, times the standard error of your sample statistic. Now the types of things we're going to find confidence intervals for are means, population means of paired differences, and then the difference between 2 population means. So an example of something that is the mean of a single quantitative variable might be something like, what is the average number of hours of TV a college student watches each day? So average number of hours spent watching TV. If you have something that deals with paired differences, you have to have some kind of natural pairing. And a really common way for that to occur is to do before and after measurements. So, for example, the mean difference in before and after weights on a diet, something like that. And then for 2 different population means, there have to be 2 separate groups. Suppose we're comparing 2 groups, so once again we're turning to a diet study. Diet versus exercise, which is better? And we tell one group they're going to go on a diet and one group they're going to exercise. So the kicker is, for the second case, is that there's no natural pairing. Unless you have identical twins and you say one twin is going to go on a diet and one twin is going to exercise. Otherwise, you just have 2 completely independent groups. So just to hit that point again, so one important thing to distinguish is to distinguish as paired data from these independent samples. So remember that paired data means that your data have been observed in natural pairs. So for example, the same measurement taken twice in each person under different conditions or at different times. That could be the before and after weight. It could be measure of your cholesterol before and after taking a drug. Similar individuals are paired before giving the treatment in an experiment, and then each member of the pair receives different treatment. So one example here could be that you could pair based on age. There was an example we discussed earlier about memory, and people were first paired based on age and then assigned different memorization techniques. You could also take two different variables measured for each individual, and there's an interest in the amount of difference between the two variables. So, for example, we could have measured, height and weight, and we care about something about how those two relate to each other for each person. So two samples are independent samples when the measurements in one sample are not related to the measurements in the other. So you take random samples separately from two populations, and the same response variable is recorded for each individual. So in that case, we could be comparing two different populations, for example, say maybe men versus women. It's a possibility. One random sample is taken and a variable is recorded for each individual, but then units are categorized as belonging to one population or another, such as male and female. So I guess that kind of is the top one as well. And participants could be randomly assigned to one of two treatment conditions, such as diet or exercise. It could also be something like placebo versus drug, or drug 1 versus drug 2. And then the same response variable, such as weight loss or recovery time, is recorded for each individual unit. So one thing you'll definitely have to be able to do is to read something and tell me if it is paired data or independent samples. So a researcher wants to estimate the difference between the mean scores on a memorization test for people who are over 60 and people who are under 40. So the question to ask yourself is there any natural pairing? And the answer is, well, unless we're testing people and their kids, then no. So this is two independent samples, as in the over 60 group is one group, and the under 40 group is another. And just to kind of preview what we're going to do next, the proper statistical symbol for the true population value here would be mean 1 minus mean 2. Women give their actual and desired weights in a survey. An estimate of the mean difference is desired. Well, since each woman has two measurements, and we care about the difference of those two, this is paired data. And the statistical symbol for that is mu sub d. And the thing is first you find the differences for all individuals. And then you take the average. Two treatments for reducing cholesterol are compared. 40 people with high cholesterol use the first treatment, and 40 people with high cholesterol use the second treatment. An estimate of the difference between the mean decrease in cholesterol for treatment 1 and the mean decrease in cholesterol for treatment 2 is desired. Okay, so in this case, there's no obvious pairing. You just have 40 people with one drug and 40 people with the other. So this once again is two independent samples. Now the next thing we need to know how to do is find the standard errors for statistics involving means, just like we had standard errors for proportions. And after we do this, once we find out what the multipliers are, we can find confidence intervals. So the standard error of a sample mean, just for a single sample mean, SE of x bar, is given by S over square root n, where S is the sample standard deviation of the n observations. Remember that S is found using this formula, the sum of all the xi's minus x bar squared over n minus 1 and then big old square rooted. We did that back in chapter 2. And the standard error of a sample mean of paired differences is almost the exact same as the one above. It's just that you first find the differences and then apply this formula. So the proper statistical notation for this is S sub d over root n, where S sub d is the sample standard deviation of the paired differences. So that what this means is that you have all of your differences, which I'm going to call d sub I, and then you find their mean, which is d bar, and then your sample standard deviation is once again big old square root, sum all the differences minus the mean difference squared over n minus 1. But the point is, first you find differences, average those differences, and then use the differences in this formula. Usually you'll be given what this S or what this SD is in the statement of the problem. So in a class survey conducted at Penn State, 175 students were asked how many hours they studied on a typical day. The mean from this sample was 2.09 hours with a standard deviation of 1.64. Find the standard error of the mean. So let's first of all figure out what information we were given. Well, the 175, that's my sample size. The mean was 2.09, so that's x bar, our sample mean. And the sample standard deviation S is given as 1.644. Now the standard error of the mean, standard error of x bar, is S over root n, which is 1.644 over root 175, which comes out to be approximately 0.124. And let's just summarize what this tells us. So if we take many samples of size n equals 175, find x bar for each. This is the approximate standard deviation of our sample, or sample means, let's say. That's probably a little bit better. As in, or, this is how much x bar will vary among many samples of size n equals 175. And recall from chapter 9 that as the size increased, the variability of the mean decreased. Those curves got more and more centered around the true mean. All right, now if we have two sample means, so two independent groups, the formula for the standard error there is the square root of S1 squared over N1 plus S2 squared over N2. And you'll be able to distinguish when do you use this and when do you use the formula for the standard deviation of paired differences, which is basically the same one as x bar. Okay, in each part, use the information given to calculate the appropriate standard error. So here we have paired differences, and the standard deviation of the paired difference is 21. So the standard error of d bar, remember that this is SD over square root of n. So that's 21 over root 49, which is 7. So 21 over 7 is 3. Now here we have two independent samples, both of the same size, both having the same sample standard deviations. So SE of x1 minus x2 bar is the root of S1 squared over N1 plus S2 squared over N2. So that's what 10 squared over 50 plus 10 squared over 50. So 100 over 50 plus 100 over 50, both of which are 2. 2 plus 2 is 4, so root 4 is 2. All right, suppose that a randomly selected sample of 64 men has a mean foot length of x bar is 27.5 centimeters, and the standard deviation of the sample is 2. Find the standard error of this sample mean and write a few sentences that interpret this value. So first, SE of x bar is S over root n, and well, S is 2. So this is 2 over root 64. Well, root 64 is 8, and 2/8 is a quarter, or 0.25. Okay, so what that tells us is that the approximate standard deviation of x bar for samples of size n equals 64 is 0.25 centimeters. So the final component we need to be able to use to find confidence intervals is something called a t-distribution. And this is the main difference between finding confidence intervals for proportions and for means, is the way the multiplier is found. For proportions, you use a z-distribution. And for parameters involving means, you use a t-distribution. And why we're going to do this is explained a little bit in the next section. But the basic idea is that there's more variability with means. You need to have fatter tails than that z-distribution has. And there is one more parameter called the degrees of freedom, which is abbreviated DF, associated with the t-distribution. And for problems involving a single mean or a mean of paired differences, the degrees of freedom is n minus 1, where n is the sample size. And for a confidence interval for a population mean, the t-star multiplier is the value in a t-distribution with the appropriate degrees of freedom, such that the area between negative t-star, so there's negative t-star, and positive t-star is equal to the confidence level. So if you want 95% confidence, this area in here is 0.95. The multiplier is the value of t such that that occurs. So and the difference between this and a standard normal distribution or a z-distribution is that these tails don't go down as quickly. So using software, a calculator, or table 8.2, which you can find with this lesson, we're going to find the value of t star for each of the following situations. So looking at that table, you see that the degrees of freedom run in the first column, and then across the top you have various common confidence levels. So if you want your degrees of freedom to be 15, notice that this means your sample size was 16, because the degrees of freedom in this case is one less than the sample size. You go over to 95% confidence and you see that the t-star multiplier is 2.13. Notice that that's a teensy bit higher than what your multiplier would have been for a z-star. And that has to do with the fact that this smaller sample size, one expects more variability. Okay, if the degrees of freedom is 30, that means your sample size was 31. 90% confidence level, the t-star multiplier you use there is 1.70. Now if your sample size is 9, your degrees, or 10, your degrees of freedom is 9. So 95% confidence level there, you'll have to use t-star equals 2.26. And just a couple things to note. As degrees of freedom goes to infinity, or as degrees of freedom is increasing, the t-star value goes to your z-star value. For example, looking at the 0.95 column. You look at that 0.95 column, as your degrees of freedom increases, you go down the column, and notice that once you have n's bigger than, say, really 60, your t-star is getting close to 2, which is what the multiplier was for z-star. And you can see at the very bottom, when you go to, it says infinite, you get 1.960 for the t-star, which was the z-star. So for 0.95 confidence level, as degrees of freedom goes to infinity, you notice that t-star goes to 1.96, which was equal to the z-star for 0.95% confidence level. So in the next lesson, we will actually find some confidence intervals for means, and then the final lesson we'll talk about confidence intervals for differences of two means.